good thing I checked, to figure out where the function is concave up and concave down. Does that make sense? So we're going to use the derivative to figure out the behavior of the graph. So the first derivative for this function is negative quantity x squared plus 4 over x squared minus 4 squared. And the second derivative is 2x times x squared plus 12 over x squared minus 4 cubed. If it was a quiz or a test, I'll just type those on the page so that you can just use them.
You'll give us the derivatives?
Mm-hmm.
Which is appreciated.
Yeah, because, I mean, it takes so dang long to take the derivatives. I mean, like, it's just taking too much time. And that was the last test. This test is, can you interpret them? Okay, so first question is to find the domain. And on your homework, please, the book doesn't state it explicitly, but label your parts A through H to make the grader's life not like a horrible nightmare. Like, the A through H are done here. Do the same things on your homework, and also in your textbook. So what's the domain here? There's two things x cannot be, and what are they? Yep, x cannot be plus or minus 2, and I didn't say interval notation, so whatever. Okay, find the x and y intercepts if this is not too difficult. So to find the x-intercept, you set y to 0. To find the y-intercept, you set x to 0. Which one's always doable? The y-intercept, making x 0. That's always really easy. You can always plug in 0, right? So plugging in 0, f of 0 is, looks like 0, right? So this function goes through the origin. When you set y to 0, sometimes solving this equation might be really, really tricky. And if it gets really, really disgusting where you're like, I've just got no clue, don't do it, it's okay. Does that make sense? That x-intercept is kind of optional-ish, and how optional depends on the situation, okay? This one you're gonna get x equals 0, so the y-intercept is the x-intercept. So, but you go through the origin, 0, 0, that's both y and x-intercept. Okay. Part C, find the symmetries, periodicity. So symmetries means, is this function even or odd? The periodicity means, is it like a sine or cosine where it sort of cycles in a predictable manner? So it's not a sine or cosine, it's not gonna have any kind of cycling going on, right? But we could check for even and oddness, right? So plug in negative x, and that gives you negative x over negative x squared minus 4. So it's odd, yep, negative x over x squared minus 4. This is odd. If for any of these parts the answer is none, state that. Like say none. Label it part D, say not applicable or none. Because if a function might not be even or odd, you say neither or none. So determine the asymptotes. This means both vertical asymptotes and horizontal asymptotes. So vertical asymptotes at x equals, what, 2 numbers? Plus and minus 2. And horizontal, you technically check by finding the limit as x goes to both positive and negative infinity of the function. And you are allowed to use rules you know from previous classes if you were sort of told what they are. So if you have x over, or you can use L'Hopital's rule, can't you? It's an infinity over infinity limit, isn't it? Yeah, so this is limit x goes to plus or minus infinity, 1 over 2x. Does that make sense? So where is this limit going to go? 0. And the plus and minus infinity isn't super important in this one. When you have positive infinity, it's going to go to 0 from positive. And as you have negative infinity, that numerator would have been negative. Does that make sense? But the denominator is positive. So y equals 0 is the horizontal asymptote. And you approach it from both sides. Okay. Determine where the function is increasing, decreasing, and find the local maxes and mins. So we had that f prime of x was negative x squared plus 4 over x squared minus 4 squared. Now, so for this stuff, you make your number line. And one thing that we didn't get to yesterday in the normal class was you also have, on the number line, you plot places where the derivative is 0. So solve 0 equals negative x squared plus 4 over x squared minus 4 squared. Does the denominator matter in that thing? No. Does the negative sign matter? No. So 0 equals x squared plus 4. Negative 4 equals x squared. And don't flip out when this happens. This has imaginary answers, right? Which means there are no real solutions. So no numbers on the number line from that. Okay, so that will happen, and students try to plot i's, and it's just not right. Don't do that, okay? Now, but the numbers that do have to go on the number line are the places where the derivative is undefined. They're technically not critical numbers because they're not defined at the function either, but your function could change behavior at those values. So those values are -2 and +2. And I would say VA below them, so you know that they're vertical asymptotes and that they're not critical numbers. And if there are no critical numbers, this function will have no maxes and mins. So it just won't have any. When you see the picture, it'll make sense, okay? So let's test numbers in f prime. So if you test something like IDK, -3. Don't test IDK. IDK isn't a good test number. If you test -3 in that expression, what's the result? A positive or negative answer? Negative. Test 0. Negative again. Test 3. Negative again. So this function is doing a whole lot of what? Decreasing. And you technically have to leave out -2 because that's an asymptote. So it's decreasing on -∞, -2, union -2 to 2, union 2 to infinity. So always decreasing.
You can only look on each side of the asymptote.
Yes.
There's no way to find if it's ever increasing.
Well, that is the way. So as in, if you,
It'd
it'd have
have to tell us there.
to tell us there, yeah. The only places that the derivative can change sign, your function can change increasing to decreasing, are critical numbers or asymptotes. Okay. Part F said maxes and mins, right? So max min, say, just make sure you say none, if there are none, because there's no critical numbers.
And there's no crits because there's no real.
There's no criticals because there's no real solutions to the derivative being 0. Exactly. And the derivative being undefined are places where the function's undefined as well, so they can't be critical numbers either. Intervals concavity. So the second derivative. Oh, and I guess I forgot one little. Okay. The second derivative was 2x over x squared plus 12 times x squared minus 4 cubed. Set that equal to 0. And can you, in your head, tell me what the one answer is going to be? So does the denominator matter? No. So you've got 2x times x squared plus 12 equals 0. So what's going to make the 2x 0? 0. Will the x squared plus 12 ever be 0? It won't, will it? It's a imaginary answer, so don't count. We live in the real world. Oh, that was a good joke.
I think so.
Oh, well, only sort of though. So we're going to do f prime prime's sign now. You plot their one, second derivative being 0 number, And you still plot -2 and 2. So those undefined places also get plotted, just like they did for the increase, decrease. They also affect the concavity. And now I think we're actually going to have some sign flippage. So look at that second derivative, plug in a test number, like say, I don't know, -3. I think negative. Do you guys agree? Because it's negative times positive over positive, right? Which makes a negative. Okay, how about a test number like -1? Negative, positive. What's -1 squared? +1 minus 4 makes -3, and then it's cubed. So it stays negative. Does that make sense? So be wary. How about +1? What are the signs of the two terms in the numerator? It's going to be negative in the end, is what you're saying, right? Yes. And from, like, say, 3, that's going to be positive. So you're concave up, concave down, concave up on -2 to 0, and 2 to 3. But no, bad. Obviously somebody needs more sleep. 2 to infinity. And you're concave down on what intervals? 0 to 2. Okay. Is there an inflection point? Yeah, f of 0 equals 0, right? Because 0 was an actual for real second derivative being 0 number. Because, yep, so critical numbers, inflection points are where the concavity changes.
Oh, and you don't include 2.
And don't include 2 for the same reason, because 2 is an asymptote. Okay. All right, now we're going to sketch. So the first thing I would suggest doing is sketching in the points you know and sketching in the asymptotes. So you have asymptotes at ±2. And what's the one point that you know you go through? The origin. Okay. Well, you could plug in numbers to figure out a little bit of what's happening here, couldn't you? Do you see what I'm saying?
It's always my favorite.
Well, like, so for example, if you plug in, let's just say -1, what's the result going to be of that? 1/3, positive 1/3. So that means your picture's living up here, right? Ish. If you plug in +1, you're going to get, I think, -1/3. Does that make sense? So f of -1 is -1 over -3. F of 1 is 1/3. And then look in between those two values. You know that this origin is an inflection point, right? What's your function doing from -2 to -2 to 2? Say that again. Yeah, this should be -1/3. Yes, it's decreasing, right? And is it initially concave up or concave down? Concave up. So it's decreasing concave up. What happens at 0, 0? Crosses and it changes to concave down. So there's where your function lives for the middle pieces. Okay, does that part make sense? All right. Now let's pick a number past 2 to plug in to figure out where our picture lives. So if we plugged in, say, like 3, that's going to be 3/5. So your picture's living, up there-ish. I specifically don't care exactly how far up, it's. And then what's it doing from 2 on? Is it increasing or decreasing? decreasing, so it has to start up high and go down. And is it concave up or concave down? Concave up, so it does this. And remember that there's a horizontal asymptote at the y-axis, so it approaches the graph approaches the y-axis, or y equals x-axis, sorry, x-axis as x gets big.
So why does it go to 0?
Because the horizontal asymptote was y equals 0. When you plug in -3, you get -3/5. Your picture lives down here. And actually also, isn't your function odd, so symmetric about the origin? Doesn't that mean that this part has to look something like that? And is that a look at that, that's an always decreasing function. Well, on its domain. That's how you, so I mean, I think, did the fact that it was always decreasing freak you out a little bit in the beginning?
No, I kind of expected this.
Okay. All right, well, okay, it would have freaked me out, but I must be special. Okay.
Broke those asymptotes, it makes sense that we start over at a high number.
Yes. Ooh, find the domain. This one has tricky domain. So roots 4 minus x squared bigger than or equal to 0. You can think about that two ways. You can think about a graph, you can think about a number line. 2 minus x, 2 plus x, bigger than or equal to 0. You test some numbers and you get minus plus minus, I think. That's the sign of 4 minus x squared. Does that make sense? You can't solve inequalities that have x squareds the same way you solve equations. It doesn't work. It has to do with sign flipping and you not being careful enough to handle it. I mean, it's just not really your fault. It's just, it doesn't work. We misled you with linear inequalities. So what numbers will work inside that root sign?
Anything from -2 to 2?
So the domain is -2 to 2. And you can verify that by picking numbers outside of that and making sure that they don't work. Like, try to plug in 3. You get 4 minus 9, which is a negative number. You can't root that, can you? Try to plug in -3, same problem, right? But -2 is okay because you get root 0, right? And +2 is okay because you get root 0. And everything in the middle, 4 minus those numbers are going to be positive. Okay. X and Y intercepts. So x-intercept, set y to 0, y-intercept, set x to 0. That one's the easy one. That gives us y equals 0. The functions don't always go through the origin, it's just that a lot of the ones we're going to graph do. The x-intercepts is not impossible. That's 0 equals x times the root 2 minus x times 2 plus x. And even though there's a root sign there, does it matter really for finding the zeros? You could just square both sides, couldn't you? And the root would go away. So what are the x-intercepts? 2 and -2, exactly. Okay, so you've got 3 points. Victory, that's more than we had last time, right? Okay, yes.
For the x in front of the root when she uses, oh wait, no.
Okay. Find the symmetry's periodicity. So let's check and see if it's even or odd. That's -x times root 4 minus -x squared. So -x 4 minus x squared. So it's odd, right? Yep. That's so strange. Determine the asymptotes. So VA, there will be none because there's no denominator. Does that make sense? HA also none, as x cannot go to plus or minus infinity. Does that make sense? Because you can't, to find an HA, you have to go to infinity in the first place, and since this function's domain doesn't include infinity, it's just, you can't even do it. So this one you just say none for both. Okay, increasing, decreasing. So I think I didn't tell you f prime yet, did I? Okay, so when I found f prime with my calculator, it gave me root 4 minus x squared minus x squared over root 4 minus x squared. That's what it told me. So let's set that to 0, but I vote for getting a common denominator. Does that make sense? That's going to be kind of helpful. What's that going to make the first fraction into? And then minus another x squared all over root 4 minus x squared. And the denominator can go away, so who cares? 0 equals 4 minus 2x squared. Does that make sense? So 2x squared equals 4. X squared is 2, and technically x equals plus or minus root 2. So in this one, when you make your number line, I'd suggest making sure it stops at the ends of your domain, -2 and 2. And then we have negative root 2. Do you guys, have you found root 2 often enough to know approximately what it is? Yeah, it's about 1.4. Like I think it's about 1.41. Okay. So here's the f prime I'm going to look at for testing. So let's just plug in 0 because 0 is nice and easy. So when you plug in 0 into what was 4 minus 2x squared over root 4 minus x squared, you get a positive result. Say that again? You get 4 over 2 is correct. Yep, which would be positive. Okay, plugging in 2 isn't an option, right? Because if we plug in 2, you get division by 0, and that's not okay. But if you plug in 1.5, what's 1.5 squared? 2.25. And then at 2.25 times 2, that's bigger than 4, isn't it? So this is going to be negative. And that's going to be negative. The denominator is positive because 4 minus 2.25 is a positive number, right? So our function is decreasing on -2 to negative root 2, union root 2 to 2, and increasing on negative root 2 to root 2. Does that make sense? If you have to use a calculator to verify, you know, what's going on in some places, just to check, that's fine. How about the local max and local min? Is -2 a min or a negative root 2? What happens there, a min or a max? It's a min. So f of negative root 2, I don't know why I just wrote root 3. This happens sometimes. And that's going to equal negative root 2 times root 4 minus negative root 2 squared. You've got to actually figure out what number this is because you're going to have to graph it. But I think it's going to work out nice.
You just plug that number in.
I just plugged that number in in the original because I want to figure out like how far up or down does this number go. And this is negative root 2, I believe, times another root 2. Is that right? Does that make sense? Because the negative root 2 gets squared, becomes 2. 4 minus 2 is 2 rooted again. And that's kind of cool because this is just going to be -2, right? And is that a min or a max? Min. So f of negative root 2. And actually, because of the oddness of the function, what's f of positive root 2 going to be? 2. You could actually plug root 2 in and do the work. All that will change is that there won't be that negative sign on front, right? Okay, great. We'll see if I can find a common denominator for you on this next one. No, I don't think I can be that fast. Okay, the second derivative that was given me by my calculator, because it didn't simplify, stupid calculator, was negative 3x over root 4 minus x squared minus x cubed over 4 minus x squared to the 3/2. If anybody wants to know how to use their TI-89 to find derivatives, I can show you after class. Yes?
Is that an x minus x squared?
Oh, that's a 4. It's just a terrible one. Okay? So what am I going to multiply to get that common denominator? Just 4 minus x squared. Does that make sense? Okay, so that makes negative 12x plus 3x cubed minus x cubed over 4 minus x squared to the 3/2. Or, do you agree with 2x cubed minus 12x? Affirmative. And then that's 2x times x squared minus 6. Is that okay? I would give it to you with a common denominator already because it's just because I didn't have enough time to before class. So set that to 0. What numbers make that 0? There's actually 3 of them, but 2 won't matter. 1 is 0, right? What are the other 2? Positive, negative, root of 6. But this is bigger than 2. As in, it's not in your domain. You can't plug root 6 into this function because you would end up with 4 minus 6, which is a negative number, so they don't count. Ha!
That's cool.
That's cool, right? They don't matter. They're irrelevant. Okay. So we have our, and if you took out a calculator and approximated them, you'd find that they're, they're a little bit bigger than 2. So, whatever, they're gone. So you might find things in your work that you think are critical numbers, but don't actually count. Like if you were doing your homework properly yesterday, you had a function that involved ln, and you found 0 being a critical number, but 0 isn't defined in ln in the first place, so throw that out. Okay. So if I tested a thing, like I tested like, say, -1. So negative first term, negative second term, denominator being positive. It looks like Kermit the Frog. So the result is positive. Okay. Test over here, and we've got like a positive, negative over positive. It's like a dead Kermit the Frog. Okay, that's going to be negative, yes? So our function is concave up on -2 to 0, concave down 0 to 2. Be there any inflection points? 0. Yep, 0, 0. Okay, awesome. Now let's actually sketch the curve. Yay, victory. Everyone's tired. It's been a long week. Every week's a long week. Okay. So our domain is only from -2 to 2, right? And I think we know that when we plug in -2, we get 0, you plug in 0, you get 0, and you plug in 2, you get 0. You got those 3 points. Zero, 0 is also an inflection. I'm just going to put a little IP there, which tells me that's an inflection point. What were your critical numbers?
0.
Square root, so root 2, so over root 2 is about 1.4-ish, right? So over 1.4-ish and up to 2, right? Back 1.4-ish down to -2, right? Those were our critical numbers, a min and a max, right? From there you can kind of see it. First you were concave up, right? Then you were concave down. It's kind of like, it looks a little bit like a sine curve, except for it's kind of skewed. The sine curve would have perfect symmetry down the middle of that little hump, but this one, the hump is a little bit to the left and a little bit to the right.
Got me so used to drawing sine waves that I can't draw.
I know, that's why I had to actually plot like 1.4, otherwise it was also impossible for me. Okay. So 3, we probably won't get to the last one, but you know, it's okay. Each takes about 15 minutes, ugh. Find the domain. So this one, domain's actually easy.
X can't equal positive or -3.
Yes, it can.
Or, I'm sorry, it's a...
It's okay, no, it happens. So think, you need 9 plus x squared to be bigger than 0, right? That's always true, isn't it? This is always true. So the domain is,
Wait, no, it can't. Wait, no.
it's okay. No, it's good to argue with yourself. If it had been 9 minus x squared, all bets are off, right? Because it's a plus, because it's 9 plus x squared.
Was that a typo?
Nope, it was on purpose.
You did it on purpose.
I did it on purpose, yep. If it was 9 minus x squared, it'd be a totally different story.
So just -infinity.
Yep, so any number, all real numbers or minus infinity to infinity. Okay, x and y intercepts. So set y to 0, set x to 0. F of 0 is going to give you 0. So once again, we go through the origin. When you find that, you found the x-intercept who. And if you try to solve 0 equals x over root of stuff, you're going to get the exact same answer, aren't you? So, okay, you go through the origin. Spectacular. Symmetries, periodicity. So find y of -x. -x over root 9 minus, or plus, excuse me, -x squared. So -x over root 9 plus x squared. That means you're odd. I don't know why I left no space for asymptotes, because that's actually going to require... Okay, no, it's down there. Ugh, I can't read. Okay, so are there any vertical asymptotes? Is the denominator ever 0? No. So VA, there are none. Oh, okay. HA, you've got to find the limit as x goes to positive infinity of this thing, and the limit as x goes to minus infinity of this thing. Technically, you can use the oddness to figure this out quickly once you know one of them, so we'll do it that way. Do you want to use L'Hopital's rule, or can I just do it the old-fashioned way we did it before? Let's review that old-fashioned way. We would have multiplied by 1 over x and 1 over x, right? And what happens to that 1 over x when it goes inside the root sign? It gets squared. So it'd be 1 over root 9 over x squared plus 1, right? So where's that going? I think it goes to 1.
I'm gonna blow up to 0, right?
Now think about odd functions. If the asymptote on one side goes to 1, where does the asymptote on the other side have to go to? -1. You can use that, okay? So if you find one, the other is opposite that. That will be true for odd functions. If the function isn't odd, those limits are not always opposites. A lot of the functions you've seen, though, do have that relationship. Okay, some work. Like, not even like increasing, decreasing local max and min. So the derivative is nice and easy for this one. It's 9 over x squared plus 9 to the 3 halves. On your sign chart, you plot places this derivative is 0 or undefined. Are there any? There's no places this is 0, right? There's no places this is undefined, right? What is the sign of this thing always going to be? It's always positive. So, always positive. So, we have this function is increasing on negative infinity to infinity. And part F, max min. Since this function is always increasing, there are none. My point with that is don't go making up places the derivative is 0 if there aren't any. It is possible for there to be none. Okay. Intervals of concavity and inflection points. Second derivative is also not so bad. It's minus 27x over x squared plus 9 to the 5 halves. So this one, are there any places where the second derivative is 0? Zero. Does that make sense? If you see an x in the numerator, you should be careful. Yes? Yeah, okay. All right, so if you test the number to the left of 0, like say -1, I believe the result is positive. Do you buy that? You test a number past 0, like 1, the result is negative. So your function is concave up, negative infinity to 0, concave down, 0 to infinity. Where's this inflection point? F of 0 equals 0. Okay, there you go. This one's faster because the derivatives were nice and easy and already simplified. This curve. So, you go through the origin. You have a horizontal asymptote at y equals 1, and also one at y equals. And I think that initially you're concave up, right? Increasing concave up. And what at the origin you change to concave down. There you go. Looks a bit like arctan, right? Except for the asymptotes are in the wrong places. Just arctan-ish. Okay, so all the asymptotes we've discussed so far are asymptotes that are horizontal lines or vertical lines. There's another kind of asymptote called a slant asymptote. I know I made you do them again. And my pre-calculus students find slant asymptotes. But it's actually not that bad. The idea is that some pictures as you go to infinity, seem to kind of become straight line-ish. And that straight line that they approach is called a slant asymptote. In similar ways, you can also define like parabolic asymptotes, like if they approach parabola shape eventually, because this isn't always a line, but it kind of becomes a line from like that point on, right? And the way you find them is you use long division. And I don't remember if we reviewed long division in this class. Did we? I can't remember.
Not in this class.
Not in this class? Okay.
I remember having to do it on the Alex stuff at the very beginning.
Okay. So it helps, at least me, because I'm super dyslexic, think about numbers. If I did 11 divided by 2, okay? When you translate that into division with the little check mark thing, it's 2 goes into 11, right? Okay. So for this thing, we're going to be putting x squared plus 1 into x cubed. Have you guys seen that? I know 3 of you have. Okay. And you do division with numbers when the numerator is bigger than the denominator, right? With polynomials, the size of them is determined by the degree. So if the degree of the numerator is greater than the degree of the denominator, you can do this long division process, i.e. the highest power. So the highest power in the numerator is 3, denominator is 2. That's why long division works. And much like here, you think, okay, 2 times, how do I get as close as possible to 11? You say that's 5, multiply, take it away, right? Same idea here. You say, how do I make this x cubed and that x squared as close together as possible? If you multiply by x, that makes it x cubed. And the only kicker is that that x distributes to both terms. Then you have to subtract it. And that negative distributes through the parentheses. And you get minus x. Okay.
And negatives.
And negatives are the bane of your existence in this process of long division. So what this says is that your function f of x is the same thing as x minus x over x squared plus 1. Kind of like 11 over 2 is 5 plus a half, right? Or 5 and a half. How could you check that you were right? You could get a common denominator, couldn't you? This undoes that common denominator process. Okay. And then what you figure out is that as x goes to infinity, where does your function f of x go to? And I don't want you to say infinity. I want you to give me an equation of a line. So does it make sense that as x goes to infinity, this part is going to go to 0?
Yes.
So f of x goes to x. And the slant asymptote is y equals x. So the component of that long division process, that is the linear function, that says for this curve, as your x's gets larger, it approaches the diagonal. So you'd have an asymptote for this function there.
I'm looking at the function. You divide the numerator by 1 over x squared and the denominator by 1 over x squared, you get y equals x.
Yeah, it does that. I don't know if, I'm not sure if that always works. Because sometimes I make problems with their coincidences. I know long division works. Without more thought, I couldn't say if your method works or not. Does that make sense? And I can't do it on the spot, so I just don't know.
So you take the one that does the same.
Yeah, and what's going to happen is that you're always going to have like a liney thing plus something that's going to 0. And the liney part is the slant asymptote. This will only work when the numerator's degree is 1 more than the denominator's, like exactly 1 more. That's when this will work. Because then the result of your division is going to have some kind of x in it. And you need an x to make a line. If it was 2 more, you'd have an x squared in there somehow, and you'd have a parabola. Okay, let's do another one. Yes?
Doesn't matter if that one degree more is in the numerator.
Say that it has to be in the numerator. Otherwise, you couldn't even do long division. Kind of like if you flipped 11 over 2, long division, then yields a decimal. Okay, so holy moly. X squared minus x minus 2 is going into 2x cubed minus 5x squared plus 3x. And the trickiest thing is just keeping track of negative signs and all that stuff. And all that matters is this first term. So what do you multiply that by to make it match 2x cubed? 2x. So 2x cubed minus 2x squared minus 4x, and then you take that away, and that negative will distribute to every term. So the 2x cubes are gone, right? You killed off one thing. How many x squareds are left? Negative 3x squared, does that make sense? And how about the whole x's plus 7x? Is that okay? All right, what would you multiply x squared by to make it match negative 3x squared? Negative 3, very good. So negative 3x squared plus 3x minus, nope, plus 6. Take away, and you get 10x. No, you don't get 10x, I lie. You get 4x plus 6. So your y is equal to 2x minus 3 plus 4x plus 6 over x squared minus x minus 2.
Minus the plus 6, wouldn't it be negative 6?
Oh, yes, it would. Thank you. That should have been a right there and there. Should have been minus 6s. Yep, yep. Okay. So as x goes to infinity, your function y approaches what line? So 2x minus 3, and so if you wanted to graph the slant asymptote, you just like plot the line 2x minus 3, you go down 3, slope 2, make it dotted since it's an asymptote. Okay, does that make sense? All right, so it really is an application of long division, and if I ask you to do a question on the quiz like this, it probably will just be to find the slant asymptote, if I even ask it in the first place. Just do the long division and say what it is. But let's actually sketch a curve that has this property in it to show us like in a picture. Okay, so find the domain. Only one thing x can't be. What's that? 0. Okay. Find the x and y intercepts. So set y to 0, set x to 0. Oh, can you set x to 0? No, so for y-intercepts, there are none. This graph will not cross the y-axis. For setting y to 0, 0 equals x cubed plus 4. Negative 4 equals x cubed. Can you cube root negative 4? You actually can't. You can't not nicely, right? But with a calculator, could you cube root it? Yeah, you can cube root negative. So in your calculator, if you have one, input negative 4 to the 1/3 power. That's how you do cube roots.
As long as it's a,
As long as it's an odd powered root, you can do negatives. So negative 4 to the 1/3, which I didn't.
Negative 1.5874.
Thank you. It's about equal to negative 1.5874. Look at our calculators give the same answer. Oh, it's because they're the same. Okay. So there we go. Symmetry's periodicity. So try to figure out if it's even or odd. I guess I shouldn't say that in a way that tells you what the answer is going to be, but you know, that's why I don't answer questions on tests. Unless is this a typo? So, do you agree if that's what you get when you plug in negative x? Because when you cube a negative, the answer remains negative, right? When you square a negative, you know, same as positive. It's neither, so there's going to be none. Okay. Determine the slant asymptotes. So determine the asymptotes including the slant asymptote.
Wait, would it really be odd if it's not? Yeah.
Oh, no, it's not odd. It's a good question, because if you had the negative of this function, the 4 has to change sign too. Does that make sense? Yeah, so for it to be odd, it would have to have been negative quantity x cubed plus 4 over x squared. Otherwise, yeah, so no, it's not odd. But good question, because yeah, it's good to clarify that. Okay, so first of all, vertical asymptote. There is one. Where is it? X equals 0. Okay, HA. Really easy, tell me why are there none?
It's X.
The numerator's power is higher than the denominator's power. Remember that? Okay. So numerator degree bigger than denominator degree. You should have learned that in an Algebra 2 and probably a pre-calculus class as well. I know my Algebra 2 students did it, and I know my pre-calculus, I mean, if your teacher didn't do it, you can go scold them. Okay. Okay, so there are no HAs. Slanty. Okay, so we're dividing x squared into x cubed plus 4. X cubed plus 4x squared. No, just x cubed. I don't know what my problem is. Take it away, and you get 4. So y is x plus 4 over x squared. Did I have to use long division for that? No, I didn't. What could I have done instead? I could have said x cubed over x squared, right? Plus 4 over x squared. Okay, so what is the slant asymptote? Y equals x, just plain old x. Okay. Because the 4 over x squared, as x gets large, that goes to 0. All right. Increasing, decreasing, max and mins. So the first derivative here is x cubed minus 8 all over x cubed. So set this equal to 0. Does the denominator matter? No, so let's just not write it. 8 equals x cubed, so what's x going to be? 2. Now when I make my number line, what else has to go on there besides 2? 0. Okay. All right. So if I plug in a number, and the whole derivative matters, so make sure you also account for the denominator because that can affect the sign of your result. So test number over here, say test -1. I think it'll be positive. Do you agree?
That's 0, and that's the vertical asymptote.
0 is the vertical asymptote, exactly, yep. Just like we had to include that in the plus minus 2 in the first example. Yep. I probably should label that 0 is the VA. What if you tested 1? What would the result be? Mm-hmm. And how about something past 2, like 3? Positive. Okay. So our function is increasing on negative infinity to 0 and 2 to infinity, right? And decreasing where?
0.
Mm-hmm. And then F, which one of those is a maxima or minima? At 2, and is it a min or a max? A min. Yep, F of 2, which will be 8 plus 4 over 4, or 3, right? Because 2 cubed is 8. Say that again.
Oh, wait, no, never mind.
Are you plugging in 0 somehow?
I'm plugging it to derivative.
Oh, I see. Yes, you must plug it into the original function. Yep. So f of 2 equals 3 is a min. Okay.
No.
And there's no max. Yep, there's no max because that's the only critical number. Okay. Ready for concavity? Intervals, concavity, and inflection point. So the second derivative is 24 over x squared. Oh, sorry, x to the fourth. It wouldn't affect your conclusion, but it is x to the fourth. So what's the only number that goes on your number line? And that's a vertical asymptote. But what happens on both sides of it? You plug in -1, you get positive. Plug on the 1, you get positive, right? So your function is concave up on -infinity to 0, union 0 to infinity. You do have to leave out places where the derivative is 0 or undefined. You can't say all real numbers because the function isn't defined in all real numbers. Are there any inflection points? Nope. None. And I think that's it except for graphing, isn't it?
There's another side.
Oh, I know that for this example.
Oh.
Okay. So, sketch in your asymptotes. So, you've got the vertical asymptote, that's the y-axis, right? The slant asymptote is y equals x, right? So that's has a slope 1, y-intercept 0. Does that make sense? So it's like this. We also know one nice point, don't we? Don't we know like over 2 up 3? So, and does it make sense that that's actually above this line? Because over 2 up 2 is on the line, right? Okay. And I think, so looking back at the analysis, isn't our function, what's it doing from 0 to 2? Is it decreasing or increasing? I think it was decreasing from 0 to 2, wasn't it? It was decreasing, and was it concave up or concave down? Concave up. So that means it's going to do this kind of business, right? And I believe that the function was increasing from 2 to infinity, right? And still concave up? So it'll look like this, and then it'll approach that asymptote. So it kind of, like if you were to graph this thing on a calculator on a computer and just zoom way out, it's going to appear to get very line-like as you go to infinity. Okay. And then on the left side, since we don't have any specific points, I would suggest just picking some numbers to plug in. Does that make sense? Like try plugging in easy things like -1, right? That's easy to plug in. That would give you 3 over 1, right? So you've got the point -1, 3. Just pick one more. How about -2? That's going to be, I think it might be negative. Isn't it -4 over 4?
Yeah.
So it'd be -1. Does that make sense? And I believe your function is increasing and concave up that whole time, right? So it's going to start down at that asymptote and increase and be concave up. And there's no symmetry because this function ain't got no symmetry. Okay? So it's a weird thing. Now what I'll do for the last example, because we are at time in 3 minutes, or 2 minutes according to that clock, I'll give you the derivatives, and I'll tell you what the picture looks like. And you can see if you can agree with that analysis. Does that make sense? That'll be enough. So for this one, the first derivative is 24x over x squared plus 4, the quantity squared. The second derivative is minus 24, 3x squared minus 4 over x squared plus 4 cubed. The picture looks something about like that, approximately. There are some inflection points in there, but it looks about like that-ish. So just verify for yourself if you want to that you can actually deduce that from the calculations. Your inflection points are not going to be nice numbers. They're going to happen at x equals plus or minus 2 over root 3. Okay.